U12 is based on intermolecular forces of attraction, and today we're just going to kind of talk about introduction to that. So there's a few things that you might want to remember or think back about when it comes time to talking about the different types of matter. There are three main types of matter that we deal with in chemistry class or in science class. It's the solids, the liquids, and the gases. And I want to take a few minutes to just kind of refresh everyone's memory about how we identify those. So for solids, right, the particles of a solid are touching, and they are organized. And so then that's one of the qualifiers of a solid. For a liquid, the particles would be touching, but disorganized. And the particles of a gas would be not touching, and also disorganized. So when you think about it, go back to thinking about the model of matter diagrams that we drew. For a solid, we would generally draw them like with a couple of particles like stacked on top of each other. For a liquid, we would draw like particles that were touching, but they were kind of like cattywampus. And then for gases, we would draw particles that were free and not touching and just kind of flying around. Okay. So that's how we would generally quantify a solid, liquid, or a gas. But today we're going to go one step further when we quantify a solid, liquid, and a gas. We're going to talk a little bit more specifically about how that relates to the unit of intermolecular forces of attraction. So solids generally exist below the substance's melting point. For example, water's melting point is 0 degrees Celsius. Liquids tend to exist between the substances boiling point and melting point. And then lastly, gases. Yes?
Don't you mean freezing point? Or melting?
I mean melting point. And then for gases, they tend to exist above the substances boiling point. And water's boiling point is 100 degrees Celsius. So these are some things that we want to kind of keep in mind. And so, yes, the idea of melting versus freezing point is something that we're going to talk about in the future. But in reality, all substances have a melting point and all substances have a boiling point. And the degree the temperature at which the boiling point or the melting point exists at has a lot to do with what holds substances together. Okay. So the next question that we're going to be attempting to answer today is why is it that why do molecules stick together? And we're going to do like I said, we're going to do our very, very best to assess that and try to figure that out. And hopefully you'll come to some degree of understanding. So there's that. Now, so why do molecules tend to stick together? Molecules tend to stick together because they are because they are covalently bonded molecules. Now, to go back in time and kind of refresh your memory, covalent bonds or covalent molecules are made up of nonmetals and nonmetals. And in covalent bonds, electrons are shared. Now, they can be shared equally or unequally, and we'll talk a little bit about that in a minute. But what really holds molecules together is something called an intermolecular force. It's an attractive force that holds molecules together but doesn't actually like bond them together. So we need to talk a little bit about the difference between intermolecular forces and intramolecular forces. So intermolecular forces versus intramolecular forces. Let's start with intramolecular forces. Intramolecular forces occur within a molecule. These are also known as bonds. And so an example might be something like this, where I would have a water molecule potentially. And this bond right here is the intramolecular force. And that would be a bond where the electrons are shared. Intermolecular forces of attraction occur between two or more molecules. Actually, I'm going to write that as covalent molecules. Which is basically the same thing, but just really trying to hammer this home. These we would refer to as attractions. And so if I was going to do my very, very best to draw what that would look like with some water molecules, I would have like an oxygen here with like some hydrogens on there. I'm trying to draw this in like 3D. So I'm going to have like another oxygen here. And some hydrogens there. But they're attracted to one another like so. And so this would be the intermolecular force of attraction. Now, since everything is about relationships, this is the example that I usually tend to give. I have a man crush on 3 people. Dwayne "The Rock" Johnson. It's not even about that. Dave Grohl from the Foo Fighters and Ryan Reynolds. I just want to be friends with these people. Okay.
I mean, The Rock is pretty built. So I mean,
Right. But like, it's not necessarily about attractiveness. It's more about like what they bring to the table. So like I have an attraction to them. So like not necessarily like anything other than like, oh, hey, like if they were walking down the street, I would definitely stop what I was doing and turn and like focus my attention on them.
I would do that with any famous person.
Yeah, but I would definitely miss any other famous person because I really don't care. But like for whatever reason, those 3 human beings I've got, like I just have this like this man crush on. That being said, I'm married to my wife. Okay. And we have a bond.
You have a crush on her?
I mean, I do, but like we have a bond, right? So what I'm getting at here is like an intermolecular force is like a man crush, right, on somebody famous, whereas an intramolecular force is like, in my case, my marriage to my wife. Do you see the subtle difference? Hopefully. Okay, so that's just kind of how I look at it. That's just what I do. Now, there are 3 types of intermolecular forces of attraction that you need to be responsible for understanding. The first one is something that we call the London dispersion force. So the London dispersion force, which has been simplified or can be shortened to LDF. Okay. Now, London dispersion forces exist in all covalent molecules. So if there's a covalent molecule present, it's going to have London dispersion forces. And that's the minimum qualification for a structure to have a London dispersion force. So this is the minimum qualification for the presence, I spelled that wrong, of LDF. If the molecule in question is nonpolar, LDF is the only intermolecular force of attraction that can be identified. London dispersion forces tend to be weak attractions, but they get a little bit stronger the more present they are. And then the total number of electrons that a structure has would indicate strength of the London dispersion force. So what I'm getting at here is that down below, I have two spheres, 2 circles, right? The one on the left is supposed to represent oxygen, and each of those like bars or lines are in electrons. So there's 8 bars or lines in the oxygen on the left and 8 bars or lines on the oxygen on the right. Argon is the 2 spheres on the right, and in argon there's 18 bars or lines in both of them, and they represent electrons. So in this case, argon is going to have a stronger London dispersion force because of it having more electrons. Now, you remember your very, very first pep rally in this high school, which for a lot of the sophomores in this class was homecoming this year? And for those of you that are older, it might have occurred at another point in time in your life. Do you remember the weird head on a stick? You know what I'm talking about at the pep rally? There's a head on a stick.
Tracy.
Tracy, that's the head's name. I forgot. I couldn't find it in my head. But at some point, I don't know, it's existed for years. It's really strange to me. Okay. But at some point, somebody comes out and stands in front of the student section and holds the head on a stick, and then everybody starts doing this. Right? You know what I'm talking about? Sorry, video, that's going to be really loud. Okay. But they start doing this. And at some point, somebody holding the Tracy head goes like this. And what does everybody do? They go this way, right? And then somebody goes like this. They go this. And then everybody goes this way. And there's like, ah. And then, ah. What? With a head on a stick? In the 4 districts that I have experienced, this is the only one I've ever seen that particular thing. And it was my understanding that it doesn't exist anymore, but I was wrong. So,
do other schools have weird stuff? Or are we just
I mean, other schools have weird stuff, but this is by far,
Not this.
of the schools that I've been familiar with, this is by far one of the most unique things.
When you say
At a pep rally.
thing, though.
One of the most unique things at a pep assembly that I've been at. The reason why I bring this up, though, okay, is because that whole head on a stick and you in the crowd interacting with the head on the stick, okay, is kind of like how London dispersion forces actually work. So before you write or draw anything, I'm going to draw something and then I'm going to change the drawing. So just don't get upset with me and start copying. So if this is an atom and I say that there's 1, 2, 3, 4, 5, let's say 6, 7, 8 electrons in this atom. What I've attempted to draw here is I've attempted to draw them as sort of spread out as possible. But before I go any further, true or false, electrons are constantly moving. True or false? True. Electrons are constantly moving. So what that means is that even though I've drawn a picture with 8 electrons and they appear to be kind of sort of spread out, they are constantly moving. And it's almost as if somebody were standing in front of them with a weird head on a stick and going like this, and then going like this, and then going like this. And the electrons actually start to shift. Ooh, I got rid of my circle. And the electrons start to shift. So what ends up happening is you might end up with a couple of electrons over here, but you might end up with an overwhelming number of electrons. 1, 2, 3, 4, 5, 6, 7. Okay, so now we've added electrons. But whatever. So we have an overwhelming number of electrons on one side of the atom. Okay? The electrons are shifting from one side to the other side, and that creates a temporary positive and negative end to this structure. So this is going to have a temporary negative end, and this is going to have a temporary positive end. Remember, that little guy right there is a partial charge from what feels like forever ago, but we definitely worked with those. So if I have 2 atoms that are near each other, one, 2, 3, 4, 5, 6, 7, 8. I think there's 9 now. 1, 2, 3, 4, 5, 6, 7. Oh, whatever. Okay, so if I have another atom that's where the electrons are sort of kind of spread out, and it comes into contact or it comes near another atom where the electron distribution is lopsided like this, the one on the left, those electrons are going to want to go away from the other electrons because negative attracts or repels negative. It repels, right? So what you really end up with is something that looks like this. And then again, this structure has a slightly negative side, and this structure has a slightly positive side, and they form an attraction there. And that's how London dispersion forces work. So you might want to draw that or kind of get that in there now. But that's how London dispersion forces work. The electrons in the structure are constantly shifting from one side to the other. And when they're constantly shifting from one side to the other, they create these subtle negative and positive charges. on a neutral structure. And those subtle positive or negative charges now become the force of attraction that we know as London dispersion forces. So now, that's essentially what London dispersion forces are. And now we're going to move into an example of how to draw and or deal with them. So, I'll give you all a second to catch up. So now we're going to use the example of CH4, which is the methane molecule. And the methane molecule, there are some things that we know about it. I know that it is a molecule. It is a covalent molecule. But there's some other things I know about it. I know that there is a carbon-hydrogen bond. I know that carbon is a 2.5 electronegativity. Hydrogen is a 2.1 electronegativity. That's a 0.4. And I remember back from first semester that anything 0.4 or lower is a nonpolar bond, right? So all of the bonds here are nonpolar. Okay. So if all of the bonds are nonpolar, then that means that this entire molecule is nonpolar. And if it's a nonpolar molecule, the only intermolecular force of attraction that that molecule can show is London dispersion forces. And so we also want to take a tally of how many total electrons this molecule has. So the total number of electrons in CH4 is there's one carbon times 6 total electrons for 6 electrons. There's 4 hydrogens times 1 electron for 4 electrons. We add that up and we have 10 total electrons. So that part of it is going to become kind of important a little bit later, because during that part of it, we are going to be making an assessment as to the strength of an intermolecular force. And the more electrons London dispersion forces has, the stronger the London dispersion force. Now, how do we draw this? In this instance, all we're going to do is we're going to draw circle A and write CH4 in it. We're going to draw circle B and write CH4 in it. We're going to arbitrarily decide that one side is a slightly negative and one side is a slightly positive. And then we're going to arbitrarily decide, no, we're not. We're going to definitely decide that this side is slightly negative and this side is slightly positive. And the reason why it's important is because opposites attract, right? So I'm going to end up with these bars of attraction, right? So these bars of attraction are indication of the London dispersion force attraction. Now, so that's London dispersion forces. And there's 2 other forces that we need to be responsible for understanding, so we're going to kind of jump into those now. The next one is called dipole forces. And in dipole forces, these are moderately strong forces that cause polar molecules to stick together. So if it's a polar molecule, the qualifier is polar molecule qualifies as dipole. So my example here is HCl. And I know that it's a molecule, a covalent molecule. Because there's only nonmetals present. I know that there is a hydrogen bonded with a chlorine. Hydrogen has an electronegativity of 2.1. Chlorine is 3.0. Subtract them, we get 0.9, which tells me that that bond is polar. So if that bond is polar, that means the electrons are being pulled toward the chlorine, right? And if the electrons are being pulled toward the chlorine, that means that this molecule itself, the way that it's drawn, is going to be a polar molecule. And as a result of this being a polar molecule, this also tells me that the intermolecular forces of attraction present are going to be, again, London dispersion forces because it's covalent, but our new force, which is dipole-dipole. So in this instance, when I go to draw this structure matched up with another one like it, I'm going to take hydrogen and bonded with chlorine. And another hydrogen bonded with chlorine. And I'm going to bond them together and then add the electrons. And so because the electrons are being pulled toward chlorine, this is going to be the slightly negative side, and this would be the slightly positive side on both of these structures. So the intermolecular forces of attraction would occur between the chlorine and the hydrogen. And so in this instance, that would be our dipole attraction. Questions? The third type of intermolecular force of attraction that you need to be familiar with is something that we call hydrogen bonds. And the problem with hydrogen bonds is that they're not actually bonds. They're just really strong attractive forces. So hydrogen bonds are particularly strong. They're dipole forces that can cause polar molecules with hydrogen bonded with oxygen, hydrogen bonded with nitrogen, and hydrogen bonded with fluorine to stick together. So the qualifier here for hydrogen bond is polar molecule with HO or HN or HF qualifies as hydrogen bonding. So what makes these particular bonds so special compared to the rest of the bonds? So let's talk about that for a minute. I'm comparing hydrogen and fluorine with hydrogen and oxygen with hydrogen and nitrogen. Oops. And when I bond these together, that should definitely be an O. Okay, so when I bond these together and I calculate the electronegativity difference, right? Hydrogen is a 2.1. I grabbed that from the periodic table. Fluorine is a 4.0. Oxygen is a 3.5. Nitrogen is a 3.0. Subtract them to calculate their electronegativity difference. And I get, what is this, 1.9, 1.4, 0.9. Those are really, really, really strong, or those are really, really big force electronegativity differences, which means the electrons in those bonds are being pulled toward fluorine, pulled toward oxygen, pulled toward nitrogen with such attraction that it almost makes the hydrogen become really positive. So the electrons in these bonds are pulled so tightly to fluorine, oxygen, and nitrogen that the hydrogen is really positive. And yes.
Is there a reason that they all go down by 5? Or is it just like have to be like that?
The question is there a reason why they all go down by 5 in terms of their electronegativity? Or just in general? Yeah, they go down by 5. Yeah. I think it's more of a coincidental issue and more along the fact of the range. No, the electronegativity difference in terms of how those electrons are being pulled toward. Okay. We generally try to remember all of this stuff by using the, acronym FONS. Like FONS. Bronze FONS? No? Yeah. Anyway, so if you see a hydrogen bonded with an oxygen in a structure, or a hydrogen bonded with a nitrogen in a structure, or a hydrogen bonded with a fluorine in a structure, that usually is an indication that there's a hydrogen bond present. And then to work through that as an example, we're going to use the example of NH3, which is ammonia. This is a covalent molecule. And it has hydrogen and, in this case, nitrogen bonding, which tells me that that hydrogen bonding has to be present. So, like, the fact that there is a 3.0 and a 2.1 giving me something like 0.9. That means those bonds are polar. The electrons are being pulled toward nitrogen, plus the unshared pair of electrons on nitrogen creates an incredibly polar molecule. So we have a polar molecule here as well. So the type of intermolecular forces of attraction that are present here would be things like LDF, because covalent molecule, and hydrogen bonding. Because of the hydrogen-nitrogen bond. Now, when I go to draw these structures together, I'm going to have nitrogen with like 3 hydrogens bonded to it. And I'm going to draw my bonds in. And I'm going to draw a second structure like that. Nitrogen with 3 hydrogens bonded to it. And then I'm going to remember that there is a partial negative and partial positive charge all kind of around this thing. And then because there's a partial positive charge on molecule A and a partial negative charge on molecule B, that's where my force of attraction will occur. So in this instance, this is my hydrogen bond attraction. Right there. Now, ionic bonds. We mentioned them a little bit earlier, and as you may recall, ionic bonds occur between a metal and a nonmetal. And the interesting thing about ionic bonds is they have those permanent charges, and those permanent charges are really what we would refer to as ion-ion attractions. Ion-ion attractions are stronger than intermolecular forces of attraction between covalently bonded molecules. Now, as an example here, right, I'm going to take sodium, which has a +1 charge, and chlorine, which has a -1 charge, and sodium has transferred that electron to chlorine, right? So the force of attraction here is really quite strong, but it's a strong attraction between the positively charged ion and the negatively charged ion. So that's why it's called ion-ion attractions. So, a little bit more and then we're done. How do we figure out which intermolecular force of attraction is present when given a structure? So this is a handy-dandy little flow chart here, okay? You ask yourself, is this an ionic or a covalent structure? Well, if it's a metal and a nonmetal, right, or two nonmetals, that should tell you something. But if it's a metal or a nonmetal, that makes it have ionic bonding, which means this is going to be ion only. If it has two nonmetals, that means it's covalent. But if it's not a polar molecule, that means it's going to be London dispersion forces, and we have to consider the number of electrons. If it's a covalent molecule that happens to be polar, but does not have hydrogen or oxygen, hydrogen or fluorine, or hydrogen or nitrogen, then it will have London dispersion forces, but it will also have dipole. If it is a if it's a covalent molecule that happens to be a polar molecule that happens to have hydrogen bonded with fluorine, oxygen, or nitrogen, that's about it. Then this would be hydrogen bonding and London dispersion forces. But if it is a polar covalent molecule that has a hydrogen bond, that has hydrogen with fluorine or hydrogen with oxygen or hydrogen with nitrogen, and another polar bond somewhere in there, then this molecule can have hydrogen bonding, it can have dipole, and it can have London dispersion forces. All of them. And we're going to spend some time tomorrow talking about or going through examples like that. Now, there's one last slide here. Where are you going? We got like 4 minutes. Simmer down there. Simmer down. So we're going to rank these types from strongest to weakest. Our strongest type of attraction is ion-ion, which occurs in ionic bonds between metals and nonmetals.
Please excuse this brief interruption. JV and varsity boys tennis. JV and varsity boys tennis canceled today due to impending weather. No practices today. Thank you and drive home safe.
The next strongest one is hydrogen bond. It's polar covalent molecule, and hydrogen with nitrogen, hydrogen with oxygen, hydrogen with fluorine. Next strongest is dipole-dipole, which is simply a polar covalent molecule. And then lastly is London dispersion forces, which is just a covalent molecule. And remember, covalents are all nonmetal and nonmetal. So strongest is ion-ion. Next would be hydrogen bonding. Next would be dipole-dipole. And weakest would be London dispersion forces. Sorry you don't have homework tonight. I'll make it up for you tomorrow.